Okay, hi. Thanks for coming out, guys. I know it's Valentine's Day and everything, so I appreciate you being here. I don't know where Mosin is. He's supposed to be here. Maybe he has a date, but he didn't tell me. I'm sure he'll come in a second. Anyways, week 6, just had the midterm. Hopefully you're feeling good about it. Yeah, slides and stuff. New classroom. It's all right. I like this building though. This building is cool. Anyways, hopefully the midterm wasn't too bad. We actually do have it all graded already. Well, for the most part, we're just going through some final checks. Um, but we should have it out hopefully end of today. So yeah, but again, hopefully you feel fine about it. The goal was to make it not that bad. So yeah. Also, I'm sure you guys have done it already, but course feedback is out. You get extra credit if 75% of you fill it out. I'm not sure if we're there yet, but we're getting close, is what Violet said. Yeah, so do that. Also, it is Valentine's Day. So happy Valentine's Day, whether you have a Valentine or not. Hopefully, I think we can disagree that we'll have fun here today from 12 to 1, and it's going to be great. To that end, I have prepared some things. So I went to Target, and all their Valentine's Day stuff was mostly out, but they did have this, which I thought was sick. It's like uh superheroes, ring pops? It's like their heads instead of the ring pop. I had one, it was gross, I'll be honest. But if you want one, it's great. I had the Hulk. Maybe that's why. Hulk. Well, just okay. The thing is, when you're opening it, you don't know who you're getting. So the Hulk is probably the bad one. That's the one you don't want. But Spider-Man's probably good. Maybe he's like strawberry flavored. And there's Captain America too. So yeah, you can have one if you want. If you don't want it, whatever. I don't know what I'm gonna do with 20 ring pops, but I'll figure it out. I also have, I thought this was hilarious. They have Lunchables candy, Valentine's themed Lunchable candy. It says, "I'm not your ordinary Valentine" on it. I think that is definitely true. So yeah, I guess you can't really share this, but someone can just grab it if they want. Uh, I I think it looks interesting for sure. There's also like little dips. You can- Where the hell is Mosin? What is he doing?
I saw him like walk.
Oh, he's coming.
So I don't know. We just passed him, and then he was walking.
He was walking the other way.
Like towards the upper, like looks like.
Oh, so he doesn't know where the room is. That's funny.
Went to go get something.
He'll figure it out. Yeah, he'll be here soon. I was okay. The initial goal, what I wanted to do today was we would have like, those elementary school parties where like you give out like cards and stuff and you like write names, and they didn't have any at Target. And Violet was like, okay, I bought my daughter a bunch, so you can have the leftovers. And I was like, that's sick. But then she's not here on campus today. So that's unfortunate. But know that I did try to do that. And that's what counts, right? Anyways, moving on. Um, yeah, homework 2, due soon. Hopefully you're finished. If not, that's fine. You have 2 days to do it. It's due this Sunday, Sunday night. Yeah, there is one transformer related question, which I know was a topic of yesterday's lecture. And can I just ask, how many of you feel very solid with transformers after yesterday's lecture?
For the homework purpose.
For the homework purposes. But overall, okay, so one, good for you. I'll be honest, my first time hearing about it, I was like, what is going on? I was so confused. I don't know. So the goal of today is to try to break it down as much as possible to really get you to understand the intuition behind everything. And also, if you need help for the homework, this should help you with that as well. Also, homework 3 is coming soon, coming out on the on Sunday. And it's due not for a while, so I'm not going to talk about it too much. It is a smaller homework than the already not too big homeworks that we've had. Most people said they took like 3 to 5 hours to do the first 2 homeworks, which is good. This one will probably be even shorter than that. So yes. Okay, what else? Yeah, so basically there's not that much to talk about, but actually there is a lot to talk about because transformers are a huge topic. I think the most important topic from this class, if you're going to take anything away from this class, I think transformers should be what you take away. And so I'm going to really do my best to do it justice. Yeah, so I think just to ramp up slowly, let's like review where we've been so far with language models, right? So we have ngram, right? Which, if you remember, treats every ngram. Mosin, you made it. Okay, where were you?
Finding this place.
Sorry, I should have told you where it was. Yeah, anyways. Yeah, so ngram, you know it, you love it. But it's not the best model. If you remember from lecture and from discussion, it is quite prone to generating ungrammatical text. For this reason, if we have a corpus, I don't know why I'm standing here. If we have a corpus that looks like this, consider like a trigram language model. This is a possible output, which is good. She enjoys playing soccer on weekends. That's good. That's grammatical. But this is also another possible output, weekends and then, right? And that's not, we don't like that, right? So not the best. Then we went with feed forward, which is similar in that there's still like a limited context window, right? But it's still not the best because there's no explicit dependencies between inputs. And we know in natural language, all words they affect each other, they affect each other's meanings, right? So it's not the best. I don't like that this chair is here. Yeah, so you know that feed forward, not the best. Even though it is a step up from ngram. Then we went to the RNN. What does the RNN do that upgrades it compared to feed forward? Just shout out. Anybody? Exactly, right? So it uses previous data to create an unlimited context window. In theory, in practice, it doesn't really do that because of problem that we've talked a lot about, which is the vanishing gradient problem, right? So to address that issue, we try to do some fancy stuff with LCM. And this is great because it does actually, in practice, create a longer context window and mitigates the vanishing gradient issue, right? And for a while, from 2014 to about 2017, this was the state of the art, right? This was as good as it got. And we started to use it for a lot of our best models, right? For something like machine translation, which was proposed by this guy, or something like seek to seek, which was proposed by this guy. It was a good application for machine translation. Okay. I'm not going to talk about seek to seek too much today, even though I know I did look at the recording yesterday. She spent a lot of time on seek to seek. I'm not going to talk about it too much because I think transformers are the more interesting part here. Okay. Yeah, so cut to 2017. This may or may not be true. I'm just going to say it because I think it is a good motivator. People start to notice that the bigger their models get, the better they perform, right? And so they're like, okay, how big can we go? But a problem comes up. Wait, where am I? Problem comes up. This, okay, yes or no? You think yes? In general, this is the case. Oh, hello? Yeah. You might worry about like overfitting, that might be an issue. But in general, we find that with deep learning architectures, this is true. But we run into a problem because larger model also requires a lot more training, a lot more difficult training. Okay. And in particular with LSTM, if we try to scale this up, it becomes kind of unwieldy to train, right? So I guess what people start to think about in 2017 is, can we somehow split this up into smaller parts and do each smaller part in parallel and train each part in parallel? Okay. Can we? How? How do we do it for an LCM? Yeah, it's really hard for an LCM, right? Because LCMs sequentially are inherently sequential, right? Each input depends explicitly on previous inputs, right? So we have to do everything in order and not in parallel. There is some, like there are some things you can do, but we don't have to worry about that too much. The main idea here is that LCM's not good for parallelization, okay? And so people were like, okay, what if we try a new architecture, right? And that architecture was what we talked about yesterday, which is transformer, right? Transformers are great. They look like this. And they allow us to parallelize our training, right? And also all the issues with RNNs that we saw, stuff like vanishing gradients, a lack of long-term dependencies are also mitigated, right? If not completely. Well, I guess there isn't an infinite context window, but it is much better with the transformer, right? So it looks like this, if you remember from yesterday. Just a stack of things called encoders, and then in some versions of the architecture, we have a stack of decoders as well. So this all comes from what is now a very famous paper, Attention is All You Need, which I was planning on reading in preparation for this to like talk about it a little bit more. I didn't get around to it, but cool paper by the people at Google DeepMind / what used to be called Google Brain. I like DeepMind better. I think it's a better name. Yeah, so cool paper. And yeah, so I just want to emphasize again that my first time learning about all this, it was tough for me and very confusing. But so yeah, don't worry if like you don't get it right away. Even after today's discussion, it might take a couple more revisits to fully understand, right? Okay, so yeah, looking at this transformer. For this class, we're going to focus mainly on the encoder part. But the good news is, if we understand the encoder, we pretty much understand the decoder as well. They're pretty similar. There's one minor difference with like an added attention mechanism, but for this class, you don't have to worry about it too much. If you want to talk about it later, we can.
Is it like the encoder-decoder attention layer that's in the decoder model?
Right, yeah. There's like, what she's referring to, there's an encoder-decoder attention, something called the encoder-decoder attention layer, right? Which is not present in an encoder. In an encoder, we only have something called self-attention, right? And the reason why that encoder-decoder attention is there is because we want to also give attention to our input rather than just our output, right? Again, for this class,
Cross attention.
right, cross attention. I mean, it's like the same thing, right?
Yeah.
Yeah. So we're going to zoom in to the encoder. There are two parts. I said one of them already. Do you guys remember what the first part is? The attention, specifically what kind of attention? Self-attention, right? So we have the self-attention layer of the encoder, and we have a second part, then you remember, feed forward, right? So feed forward, basically just a multi-layer perceptron. These two parts make up the encoder of our transformer. Again, for this class, we're mainly going to focus on self-attention. There are, I guess, some interesting things about feed forward. I watched a video last night about it actually. There's like a theory that like all the actual knowledge is captured within this feed forward layer, right? Anyways, we don't have to worry about it too much. The self-attention is what we're focusing on. So what is attention? Do you guys remember word to vec? Word to vec was like our way to generate dense representations of words, right? And at the time, we had to believe that this was the best it got. So it's as good as it gets. But word to vec does have a big problem, right? Right. So if we look at this word, right, say we have some word to vec generated representation of it, like this, and say this is the context for that word, right? Did you mean to the right or to the left? That's fine. We don't see any issues with that. This looks great to me. But what if we have the same word in a different context, right? You're okay, right? Is this right and this right semantically the same? No, right? So we probably don't want the same representation for these two words. We want, based on the context, to somehow update the representation, right? That's not good. But what we do is we look at the words in context. We have two here, left. These words probably indicate that, I mean, not necessarily, but probably indicate that the right here is like the direction to the right, right? Whereas, I'm kind of stretching here, but this comma indicates we probably mean like the confirmation, right? Right? So what we do with attention is we look at all the context words, looking at some central word, and then we update our representation of the central word based on the context words. Does that make sense? Yeah.
So like for like the generalized n-gram model, when you're training the word embeddings, aren't you also considering like context? So like how is this sort of like different?
You said for n-gram?
So like before.
Oh, I see. I guess you are also considering context in that case. But the problem with feed forward is it doesn't scale very well, right? If you try to create a large feed forward model, performance will always be much worse than a transformer, right? So the transformer just improves that. Also, I don't think you can parallelize feed forward as well. So that's a benefit. I think so. Feed forward does create contextualized embeddings, right?
Yes, but only for a small context window, so only a few words like before and after it. If it's like a long dependency for the meaning, then it can capture that.
Right. So that's the benefit of a transformer over that. That's a good question though. Yeah, so this is what attention is doing. It's looking at relative to some central word, we want to update the meaning of the central word based on context. That's it. Okay. And just some terminology, which to me is a bit confusing. For a central word, if a context word affects that central word, we say that the central word attends to the context word. I don't know why it's in that direction. I feel like it should be the opposite direction, but this is what everyone says. So in this case, right attends to left, right attends to two, etc. So just be aware of that. Also, okay. Yeah, so this formula came up in lecture. To me, just looking at it, I'm like, what is going on? I don't understand. I'm gonna try to break it down as much as possible. The intuition behind each step, as much as I can. Okay. So first of all, well, if you remember, look at this. If you remember, we have three, well, I guess more than three, but in this, for relevant to us right now, we have the query matrix, the key matrix, and the value matrix, right? So I'm going to go through each one. What exactly is a query? I want to give you, come on. I want to give you an intuitive idea of what it is, because I think at least for me, that helps me understand it better. Basically exactly what it sounds like. It's a question being asked about a word's context, right? So in the case of the word of the sequence before, do you mean to the right or to the left? The question might be, are there any direction words in context, right? So if there's a direction word like to or left, that's what the query is asking about. To be clear, I want to say that the query is referring, is closely related to the central word, right? Not any of the context words. It's related to the central word. The central word is asking, are there any direction words in context? In reality, this is like a simplification, but I just wanted to give you like a concrete question that I might be asking, right? Okay, so if you guys remember from yesterday, we get our see pointing, but what are you pointing at? Exactly. Yeah, so we a weight matrix WQ with our embedding for our word, and then we get our query vector, right? So just a reminder about that. So given this vocabulary, hot and dog, we can package this vocabulary into one matrix. I'm just going to say this is the vector for hot, this is the vector for dog. And then so we have two words, and each of them, the embedding dimension is 3. Okay. And this is some arbitrary WQ matrix. If we multiply these two together, we get our set of query vectors. So what do you guys think each row of this represents? Each row of this query matrix. If this is each word, the embedding for each word, what is this? And as a reminder, the query vector is like a question that a central word is asking about its context, right? Yeah. Right. Yeah. So each row is just the query vector. It's asking a question about its context. In this case, this is the query vector for hot. This is the query vector for dog. Right?
Wait, can you please clarify how the WQ the matrix is?
Yeah, so this is initialized randomly at the start, and then through training it's updated and optimized over time, right? So it's completely like random right now. Okay, any other questions? Clear? Cool. All right. So now moving on, so that's the query. Query is asking a question, right? We also have a key. Intuitively, you can think of it as like an answer to that question, right? So if the query is asking, are there any direction words in context? A key might be saying, yes, I am a direction word. Pay attention to me, right? And in this case, the way that we represent like the answer yes is if those two vectors align in the same direction, right? Okay, so if we have this query, are there any direction words in context? This is our central word, and then we're going to look at the key vector for each of these, right? So I'm just going to plot it up here to make it more clear. We have the query, which is pointing in this direction. That's the query vector for the word right. And then the word u, this is the key vector for this. You can see that it doesn't really closely align, right? Which is what you would expect because u is not a direction word, right? Then we have two. Two is kind of a direction word, so it more closely aligns with the query. Same thing with the other two. And then we have left, which is a direction word, and then it closely aligns with the context. Obviously, this is like a bit of a simplification, but this is kind of what you can imagine is going on behind the scenes, right? So again, if a context word does answer the question, yes, no, whatever, it will closely align with it, right? Okay, so yeah, this is the same thing. We have a primary matrix WQ, we can get our, or sorry, WK, we can get our K matrix by multiplying the weight matrix and the embedding. Okay. So same thing as the query. Okay, so we have this idea of questions and answers with the query and the key. And we also have this formula. So what exactly, I want to zoom in here. What exactly, like, why are we doing this, right? Why multiply Q and K transpose, right? Does anyone have any guesses so far based on this right here? Yeah.
You highlight the contents of it.
Right. So basically, if we have a query matrix, looks like this. I didn't want to write it all out. If we write each row here as just a vector, Q1, Q2, Q3, etc. Let's say this Q1 represents the word did, Q2 represents the word you, etc. Same thing for the Ks. If I multiply these two together, this is what it looks like, right? I'm taking the dot of each query and key possible, right? Do you guys remember cosine similarity, right? That's basically what's going on here. I'm seeing, does each query closely align with each key, right? So yeah. So this will give us the similarity between every possible pair of query and key vectors. Okay, is that clear? Yeah.
With the key vector, that corresponds to that second sentence you have, right? The question, like the representation for that.
Sorry, the query or the key?
For-
The key corresponds to words in context, right? So if I go back here, this key right here is a representation of did if it's in the context of some central word, right? Whereas we consider like this 1, 2, 3, 4, 5, 6. Q6 is the query vector for right when it's the central word, right? So basically what this is doing, I don't have Q6 listed here, but you can imagine if this entire row is showing for the word right, for the query right, this is how much the context words answer the question. Does that make sense? Yeah. Okay. So just to like really nail it in. So say that this is I'll just change it. This is mean, Q3, mean, right? So that's the central word. Q3.K1, that is basically the answer for the question, how does did affect mean, right? And then K2, how does you affect? And then Q3, K3, how does mean affect mean, right? And so on.
So where's the query question that's being represented?
Where's the query being represented? It's in each of these Q vectors. Right.
Okay.
Yeah. Clear? Okay. Yeah, so basically this will give us between every possible pair of query and key vectors, the similarity between those two pairs. That is basically telling us how much each context word affects a some central word for every possible word. Okay. It's confusing, I know. So we call these attention scores kind of, not quite. We have to do a little bit more to it to get us there. But we will get there soon. Okay, so one more illustration. I spent so long making this. So we have some query, or sorry, some sequence, input sequence, I mean to the right. right? Basically what we do to calculate these scores is we start off with the query with considering I as the query word, right? And we want to see how much each of the context words affect I, right? So we're going to look at mean to the right. In this case, let's just consider the query to be like, how much does this word affect my meaning, right? Something simple like that. What, I mean, I guess there's no easy answer for this, but I just chose mean to be the word that affects it. Okay, so mean affects I a lot, so we add in. I'm just going to indicate like a large dot product as like a green color. Okay, and all the other ones that are blank are small. Okay, so I's meaning is affected by mean. If we go on to mean, we again look at each of the context words, and we see how much those words affect the meaning of mean. Right? In this case, just I. Again, the actual, I guess, just my guess. I don't know what actually would affect the words. So we can go on to 2. What do you guys think might affect the meaning of 2? Which words? The. Right. I think, yeah, both the and right affect two's meaning a lot. So let's just zoom through the rest. So the affected by 2 and right affected by 2 and the, right? So again, these are all just dot products. Okay. Hopefully that is clear. Okay, so what's the next step after this? You guys remember based on the formula? What is DK?
The dimension of the. Like the hidden dimension.
Right. So by hidden dimension, I found that very confusing. Yeah.
Wait, so I actually asked her this question in class. I asked her like, it said key matrix on the slides, and then she said that the hidden matrix is the same as the key matrix. The dimensions are the same.
Right. I think the only time when that's not true is from my limited, you can correct me if I'm wrong. The only time when that's not true is in multi-headed attention. You have to be more careful. I don't think we're going to get into that in this class, but I think in multi-headed attention, the hidden dimension is not always the same as a dimension of K, because we have a bunch of heads. All the different Ks for each head is are concatenated. Right.
So I think it might be misleading because it's like DK versus DH, you know?
Yeah, I don't know.
Also,
It is very, I was so confused by this originally. But it is, for our purposes, for single-headed attention, DK is the dimension of the key, which also happens to be the dimension for the query, which usually also happens to be the dimension for the value, although not necessarily. Just look at, when you're doing problems, just look at the key matrix, okay? Cool. Yeah, so we do this because it makes optimization easier. If don't ask me why it's the square root. Yeah. So
I'm sorry, I had a question from the last thing. So basically, I was just wondering why the word vector needs to be multiplied by WK to get the query. I just don't understand why you can't just multiply the word itself by the.
stop me when I'm at the
Or you're
right part.
you're fine here, but why can't we just multiply a word vector with K?
You're asking why do we need to do the matrix multiplication?
Or why do we need to have the one for the query, the query matrix? I don't really understand.
As opposed to multiplying the word embedding with.
Yeah,
So the query.
because it's randomized at the beginning, so how
Right.
is that a query? Or I don't know.
I think it's important to realize that it's important to understand the semantic idea behind each thing, right? The embedding is the word representation. We don't want to mess around and have it represent two different things, right? Because that gets messy. The query is always a question that the central word is asking about its context words. How much should I pay attention to the words around me, right? I mean, maybe you could try to make a transformer model that uses the embedding here instead. I don't know if it would work very well.
And then since like the two vectors for both the query and the key are randomized, how do you know, like, I guess you just have to learn the similarity over time? As
Yeah,
in the
through
sense, like-
optimization,
Okay.
you eventually come to like a good
Okay,
representation. Yeah. Question. Yeah, so again, relating to dividing by square root of dk, I think they just found that this works well. It makes it so that we can scale down these values, right? If we have, so you guys remember softmax, the way it works is it takes a vector, and it, say there's two values in the vector, 0.01 and 0.99, or sorry, let's say 0.3 and 0.7. The further apart those two values are, the further apart they'll be pushed by softmax, right? If they're like, one is very small and one is large, they'll be pushed very far apart, and that's difficult for optimization purposes, right? So that's what we're doing here. We're trying to scale them down so that it's not as like spiky. Is that clear? Are
Is
you
DK in this case 6, like 2 by 3?
DK in this case would be 3. Why do you think 6?
Well, because each query vector for each embedding would be 3 by 1.
Right. So this is the transpose of K, but I mean K also looks like this. So this is the hidden dimension, right? Okay. And then another thing we also want to take, very importantly, the row-wise softmax. I actually made a mistake in these slides. I did all of it thinking that it was column-wise, and so I had to redo all of my like animations and stuff. It was very sad. I only realized at like 11:30 last night too, so it was bad. So yeah, it is row-wise softmax, not column-wise. And by row-wise, I just mean, say I have a matrix like this. This marker is dying. I'm doing it in that direction, right? What does softmax do? Normalize? How?
It makes all the numeric inputs turn into like probabilities to add.
To add to 1. Yeah, exactly. I do have this video. I love this video. You guys know 3 Blue and Brown? He's great. I thought it would loop, but it does not. So this is pulled from his video. Basically, this is, he has it set up a little differently where he's doing it column-wise. You can just flip it in your mind. Imagine these are the queries, these are the keys. Then you want to do the row-wise softmax, right? But yeah, he's going row by row, or sorry, column by column in this case, and applying softmax. Okay. Cool. So that's keys and queries. Does that make sense? What we're doing? Hopefully, yes. We also have values, right? So the way I like to think about it intuitively, I think it's a little different than what Violet said, but I think to me this is what makes sense. I like to think it's like if a word is in context and it's relevant to some query word, the value vector is what should be added to the query word's embedding. to update it to make it so that the query word is affected by the value word. Okay, that probably doesn't make a lot of sense, but we'll talk about it more. Okay, so basically, this is like another way to think about it. It encodes the context of the value embedding, the context that that value embedding will provide. Right, so in this case, right is the central word, the query word, right, and left is the key / value word. The key and value word are the key and value, as you would expect, are like correlated, right? They go along, they're like pairs. So if we have this query word, this query vector, this represents the query vector for the word right. Then we have this is the word embedding for the word right. And then we have the key vector for the word left. This blue line right here is the value vector. Okay, so basically, if I take this value vector and I add it to my embedding, if I add it to my embedding, it gets me closer to updating or to like an updated value, an updated representation of the query embedding, right? One that takes into account its context. Okay. There's some examples. I have the phrase big red dog, right? I take dog, the embedding for dog, I add the value vector for red to it. This is a context word, and it updates it to a contextualized representation, a red dog. And if I take big, the value for big, and add it to the embedding for red dog, what is now a red dog, it'll give me a big red dog, right? Make sense? This is a little different than what Violet said. I just think this makes more sense to me. Yes, okay, so going through, this is our same example from before. I mean to the right, and we calculated all of our attention scores, right? I'm just gonna fill in some random numbers. Notice that row-wise, all of these add to 1. That's important, that's what softmax does, right? 1, 1, 0.5, 0.5 adds to 1, etc. These are all just like random, doesn't really matter what the actual values are. Okay, so we remember our formula. There's one final step, which is to multiply by our value matrix, which again, just like our Q and K matrices, we get it by multiplying our embedding matrix by our QV, right? Yeah, so once we do that, once we have our value matrix, we can multiply it by the attention score. I'll just call this the attention score matrix. Is it clear why I'm calling that? Okay. The attention score matrix is this big thing right here. So this is what I end up doing. So these are the value vectors. So it's like the row-wise vectors. And these are the attention score vectors, right? So I end up multiplying. If I do this multiplication, this is kind of what I'm doing, right? Before the first value was 0, right? So 0 times vi, and we go down the line, right? So yeah, you can see in this column, each value vector is the value vector for me, and the same is true for all the other columns. Okay, how are we doing on time? Okay, yeah, so what's cool is that we can take the sum row-wise of these things, and it shows us which I guess which words in context each central word pays most attention to. All right, so this is called an attention pattern, I believe. And this is what it looks like. So in this case, for the word I, the word mean affects it. We can tell because in our sum, we see this, right? If we just go down the line, we get 0.5 times basically this plus this, right? And et cetera, et cetera. So for each for each word, for each central word, we can see which words affect it the most, right? So I is affected most by the word mean. Mean is affected most by the word I. To is affected most by the words the and right, and etc. Okay. So what's really cool, like I said, is if we add each sum to our original embedding, we get our contextualized embedding, right? So we've accomplished our goal basically at this point. Okay. So that's a lot. I know I've been talking for like 50 minutes, which is crazy. I usually I don't talk this much. I feel like transformers are like just a special. I want to like really dive deep into it. And also there's not that much other content this week. So yes. So this is, if you remember, this is our formula. So I'm just going to go through just to remind you what each part is doing. So for our query matrix times the transpose of K, this is getting our basically our answers to our questions, right? Then we're scaling down to make optimization easier. We apply softmax row-wise to get our weights, right? Oh, something I forgot to mention. The reason why we apply softmax here is because we want to take a weighted sum over all of our value vectors, right? Because we want to like basically get the average amount that we should update from each word, right? And we weight each word differently based on how much we should pay attention to it, right? Okay, so that's what's going on there. And then we multiply by our value matrix to get basically what we should update, right? And finally, we can add this. We take the sum row-wise, we can add that to our contextualized embedding, or we add that to our embedding to get our contextualized embedding. Okay. Let's have a quick here. Up for a lot.
Vector, you have to multiply by all the other vectors.
For each like query key pair, right?
Yeah, each query key pair.
Exactly. Yeah, so it's L squared because how many query vectors do we have? If L is a sequence length.
L.
L. How many key vectors do we have? Also L. So it's L squared because we want to get the attention between all of them. Okay. Cool. Okay. People, I noticed in feedback, people want a lot of calculation questions. Yes.
Wait, so on the previous question, so after you do the calculation, you said you add that to the word embedding. So,
Wait, what?
so if you go back to the previous,
Yes.
you said that you do the calculation and then you add it to the word embedding.
Right.
That's a residual connection that happens after the subtension.
Right.
So the computation would be L squared plus L if you add all the computation to the word embedding.
I guess that's not strictly considered part of attention. Right. That's like,
Yeah, that residual connection is like completely after self-attention. So like this question was only about the computational like time for self-attention itself. Okay, it's just a simple addition. So even if it was there, it would still be L2, I think.
yeah, even if it was L squared plus
It
L,
would still
right,
be
it would still,
I just was wondering if that was still a computation. Is that no?
yeah, it doesn't make that big of an effect on the final complexity. A good question. Okay. Yeah, so for this vocab, which we saw before, hot dog, we have, I'm just gonna, who's finished homework 2? Okay. Well, this should help you a bit. So, do you guys remember given some vocab matrix in each of these weight matrices? How do we get our query, key, and value vectors? Yeah, multiply them. So for Q, we take our matrix. I'm not gonna show you all the. I assume you guys remember how to do matrix multiplication. If not, you can use a calculator like I do every time. Yes, okay. So we multiply x by w cubed, and this is our result. Since each of these are actually the same, this is just the same calculation 3 times. Okay, so we have our q, k, and v. Okay, so now we can use these. I should briefly stop and check. For each of these vectors, for q, what is each row of q? Say this first row. What does this first row represent intuitively?
The query goes to the first word.
Right, for the word hot, right? And then for key, for the key matrix, what is that first row? So again, to remind you,
And the key vector for the first word.
the key vector for the first word. And again, so the query vector is like a question that we're asking, right? How much should a central word care about its context words? The key is like, if I am a context word, I'm answering some query, right? And then the value, similar thing. This first row here is the value vector for hot. But what is that intuitively? Basically, it's how much. Again, this is my interpretation. How much, if a context word is relevant to a query word, how much we want to update the query words embedding, right? Hopefully that makes sense. If not, you can stop me. Okay. Cool. Okay, so if we consider dog, which is the second word, as the query word, what are the attention scores in this case? So how do we get the attention scores?
And transpose can multiply q by the transpose.
Exactly. Yeah. So we take q and the transpose of k, multiply them together, we get this. These aren't quite the attention scores yet. We also want to scale by our dk here, which again, dk, the reason I know this is word 2 and not some other values because the hidden dimension here is 2, right? So I'm scaling by root 2. And then I take softmax, which the formula looks like this, and I apply it row-wise over the rows. And it gives me a nice little distribution for each row. You can see that these add to 1, these add to 1. Okay. So those are the attention scores. Is this clear?
Wait, for dog, if dog is, it's hot dog, right? So if dog is the third word, is it the second row? That's the attention scores.
That was going to be my next question. Yeah, it is. It is dog. I also saw a question back there.
The row term is the vertical term.
It's the number of columns.
Oh, okay, so it's the horizontal dimension.
Right. Yeah. Yeah. So these are the attention scores for the word dog as the query. And you can imagine these are the attention scores for the word hot. If I really want to zoom in here, I can go even further. I can say, what does this 0.01 represent? It's the attention score of the word dog as a key on hot as a query, right? And this is dog on dog. Make sense?
So the final answer is the second.
Final answer is the second. Oh. Okay, so now going to this final step, which is the goal of attention, right? What is the contextualized embedding? The new contextualized embedding for dog. So we have our attention scores, we have our value matrix here, and we have our vocabulary matrix. That's X. Could call it V because there is a V already. Basically, the first step is, if you remember from the formula, just to multiply our attention score matrix by V. This is what we get. And then we can take, this is what Mohsen is referring to with the residual connection. This is what's happening in the residual connection. There's also something called layer normalization, which I think Violet will talk about. Not, maybe she'll talk about it next Tuesday, briefly. It's not that important for our purposes. So I omitted it here. But yeah, basically we just take the Z, we add it to our vocab X, and we get our new contextualized embedding right there. This is a new contextualized embedding. Cool. I think so. Hopefully that makes sense to you. Again, this all took a long time for me to wrap my head around. Very confusing to me. So I would understand if you still have confusion. I would expect it, honestly. There are some final issues that transformers do need to consider, but which we will not talk about for the sake of time because we are already at an hour. Basically, I think Violet will talk about this actually. The whole draw of a transformer is that we can process inputs in parallel, right? We can do things, we don't have to do things sequentially like in an LSTM. But then if things are all happening at the same time, how do we know what position each word is in the sequence, right? Because that's important, right? The sequence, I like cats and cats like I, semantically very different, right? So we need some way to capture the what's it called? The positions of each word. That's what positional encoding does. We'll see that in lecture slides. We might also talk about it later. I can't remember if we will be asking you questions about it, but if we do, then we'll be sure to cover it in more detail. Also, layer normalization, that's what I mentioned earlier. Another issue related to residual connections and actually updating our embeddings, right? There's also the whole thing with like the feed forward layer, like why do we need that? What's the point of it? We're not going to focus on it here, but it is something to consider. There's also the whole idea of the decoder, which we didn't even talk about. Good news is, again, it's basically the same as the encoder, it's just one little block that's added to it. Oh, interestingly, I should say, there are some, like GPT, for example, only uses a decoder. Doesn't even use encoders. So that's, if you're interested, you should look into that more. Also, there's the issue of multi-head attention, which I think Violet did touch on briefly. I might talk about it next time. But basically, it's just it's just a way to scale up the transformer to add a lot more parameters to make it more performant, I guess. Simplification, but yeah. Also, there's the idea, like, how do we actually train this thing? Like, the whole goal, the whole reason why we want to use this is because we can train it in parallel. How do we actually train it in parallel? Another actually non-trivial thing, but we won't consider it for this class. I did want to mention it briefly. Okay, that's it for transformers. There's also, yeah, Wilson, do you want to?
Okay, so we are in the process of designing the homework report, and it's going to be about LLMs, but we also want to know your feedback and like what do you want to see in it, what do you want to work on, what do you want to learn about LLMs. If you have any feedback, please tell us.
Yeah, you can tell us now, or like send us an email, something you would like to see. I did see some people mention in the feedback form they want to see like fine tuning. So we can, that's something we're considering, right? But also in particular, like, are there any like applications of LLMs that you would want to consider something to think about as well? And we'll try to take everything into account. Okay. Yeah. Okay. Yeah. So that's it. Hopefully that was good. This is the Hulk, by the way. It's so bad. It reminds me of you know those SpongeBob ice creams? That's what it looks like. The hair tastes so bad. It's awful. So you can have one if you want. Also, highly inspired today by 3 Blue 1 Brown. Great videos. Can't recommend more. If you are still struggling and want like a really good intuition behind everything, Yeah, that's it. So thank you guys for coming. Hope you guys have a good Valentine's Day, and I promise next week, if you come next week, will be less lecture-ish than this. Okay, sorry, give me 1 second. I'm just gonna stop the recording if I can figure out how to do it.
Yeah.
End meeting.